We're starting a little bit late today, but it's a short lecture, so at least there's that. So today's our last topic of environmental radiation, and we're going to focus on strontium-90 and its daughter isotope yttrium-90. There's no reading for this, and it just follows on the discussion we've been having already. We've already talked about strontium-90 as being one of the main fission products of both uranium-235 and plutonium-239 fission. And some of this is produced by itself, but it's also a daughter product of this. So we get kind of a double whammy of that. So we're going to talk a little about some of the sources to the environment, which primarily were above ground weapons testing is one of the major fallout nuclides because it's relatively long lived. It's 29 years. So we've still got something like a quarter of what went into the atmosphere is still alive from radioactive decay. It's a waste product of nuclear power. It's used in medical processes, radioactive thermoelectric generators, which are oftentimes most famous for being things that are put into spacecraft and launched into space that gives them power when they're very far away from the sun. They're also used a lot in locations that are like high northern latitude outposts, lighthouses, etc. Nowadays, we don't use strontium-90 in them anymore, but in the olden days, they were like the main source. And as we'll see, these have gotten into the wrong hands, especially in the former Soviet Union, which became kind of a Wild West attitude and mentality after the fall of the Soviet Union. So a lot of this stuff fell into the wrong hands. Then we'll talk a little bit about environmental pathways and toxicology, and then environmental monitoring, primarily looking at teeth, baby teeth, for instance, because it's transferred into the food web through milk. So just a few facts about strontium. This is an element that was discovered a long time ago, 1790. It's oftentimes used in fireworks because of this red colorant. It's got a lot of stable isotopes. Strontium-80H is the main stable isotope, but some people know about it because of its radioactive form, 90. It has this half-life, which we mentioned, of 29.5 years. It emits beta particles, and it decays to yttrium-90, which then has a half-life of 64 hours. So if you get this in your body, and you ingest it, and as we'll learn, strontium accumulates in bones because it's so similar to calcium. It can then not only produce radioactive damage by decay, it will produce double radioactive damage by a second decay that happens in situ. With obviously much shorter half-life. We've talked about this diagram a bunch of different times. This is the uranium-235 fission spectrum. Strontium-90 is on this side of the lower energy peak. We've also looked at this nuclear cascade from high-level radioactive waste before. Here's strontium coming down. It's got a kink in it because, so it starts to decay, but then it's got a kink in it because it also produces yttrium. Yttrium has its own curve because it's also produced in this process, but more of it is produced when strontium decays into it. So yttrium also has a kink. And so you can see that, even over a time scale of multiple decades, there's still plenty of this stuff around, and we still see it as a principal component of the nuclear fallout. So strontium-90 emits beta radiation, is ionized radiation, is a pretty radioactive material, 138 curies per gram. The energy of the beta particles is pretty high. So not all beta particles are equal. The higher the energy, the more disruptive they are. And some of these are very high energy, which is what we call hard betas. And it decays into this yttrium-90, which is also a beta emitter. And that beta particle is even higher in energy. And so it's partly what makes strontium-90 so disruptive. So in materials that have been sitting around for a few times the shorter half-life of the pair, they are decaying at the same rate, right? There's no extra yttrium. And if there was less yttrium to start off with, they start to reach a condition of secular equilibrium where they're decaying at about the same rate. Okay, and that doesn't take very long, usually about 5 times the half-life, something like 12 days. So strontium is really similar to calcium. You can see it on the periodic chart. It sits right below it. Everywhere where you have calcium in your body, your bones, your calcium ion channels, strontium can substitute for that very easily and become pervasive in the human body. Teeth is another place. So it has a way of becoming embedded in the structure and therefore not flushed out of organisms such as humans, and that creates an internal radiation source. So strontium can be an external radiation source because it's got this hard beta. So if you come up on an RTG or something like that, you can be exposed from it. But if you get it into your body, whenever we have internal radiation sources, these are much more dangerous because the radioactivity is fixing within your body. So is ionizing radiation, which we've talked about before. Ionizing radiation means that it can kick electrons out of molecules, it can disrupt bonds, it can interact with tissues and cause tumors. So this is just an above ground test from the United States in Micronesia in the 50s. We introduced a lot of strontium-90 and yttrium-90 in the atmosphere, as did the Russians during the period of above ground nuclear testing. We also produced other longer lived isotopes like cesium-137 and similarly lived isotopes, strontium-90 like tritium, which we talked about last week. But there's huge flux of these things still coming out of atmospheric particulates. Because of that, there's huge quantities of strontium-90 in surface soils around the world because of that fallout. And you know, obviously very close to the sources. I showed you those radioactive decay contours, you know, a couple lectures ago. But you know, some people who live or work in and around the area of the above ground tests did experience exposure and gave us test cases to sort of learn about what the exposure was like. Other things about strontium-90 to know is that it's used in medical imaging devices. So not all medical imaging, but certain medical imaging devices use it. It's becoming less and less common, but it's still common. Also, sealed strontium-90 sources are used to produce X-ray beams that can treat cancer. Again, becoming less common. It used to be used in luminous signs that were, you know, things like exit signs that were put up away from places of power, nuclear batteries, industrial gauging. Sort of, I would say, you know, in the early days when there was a lot of strontium-90 around, people were trying to find uses for it, and they weren't so clear on what the risk factors were. It was getting into a lot of different materials, including RTGs, which, as I said, are radioisotope thermo electric generators. They basically convert heat energy, heat released by the isotopes, into electricity. And these were used in a lot of different things. Nowadays, RTGs are not based on strontium-90. We still have RTGs, but they're based on much longer lived and much more stable isotopes, typically plutonium-239. And an RTG, it depends on what it's being used for and so forth, but they can contain several hundred grams of strontium-90, which is really radioactive, and microgram levels can be toxic to the human body. So this is just an example of some Russian RTGs. These were kind of notorious because they use these things all over the place in sort of outposts. You know, and they weren't the only country. We had some RTGs like in Alaska and so forth at lighthouses and radar installations and other places where we needed that continuous power. But we kept track of our stuff. At the end of the Cold War, these things basically mostly went missing. There's all sorts of cases in the literature, like fishermen or other people just like, oh, what are these? And taking them apart. And sometimes just for the scrap metal, not even knowing what's inside and getting exposed and being killed and so forth. And you can read all about it. This is a really long article that goes into the detail of this history, but it's a fairly well-known thing that there's a lot of strontium-90 now not accounted for, and it can be used for all sorts of different applications, including dirty bombs. It doesn't take very much of it to create a dirty bomb. So that was an example, for instance, the Republic of Georgia, which is one of the former Soviet states, where a couple farmers or hunters or whatever, I should say, came in contact with one of these things and they became irradiated, and they didn't even know what it was. So, you know, when the Russians were making those models that we looked at on the last page, they were putting on something like 1,100 to 6,700 terabecquerels of strontium-90, right? And becquerels a count per second. So these are really, really high quantities of a high level hard beta emitter, something like 4 to 8 sieverts, which, if you recall, is a lethal dose, right? And so for something like 50% of the population, around 6 sieverts, that's a really intense radioactivity. And that's at 0.5 meter away. That's standing away. And obviously, radioactivity decreases as with distance from a source. So, and that of course decreases to something like 1 to 2 at a meter, but a meter is not that far. If you come up on something and you start pulling it apart, you're getting a high dose. So, all it takes is something like 10 micrograms to inhale. 10 micrograms is 10 millionths of a gram. And these things contain hundreds of grams. So you can irradiate an area and contaminate a lot of people if you get your hands on it. So nowadays, people use plutonium. It's more common to use plutonium-238 than 239 because of the short half-life isotope. Plutonium-239 is a long half-life isotope. They need a lot less shielding. And so, it tends to be a much more stable metal. So recall that we also talked about the fallout, the global fallout, both in wet deposition and dry deposition. Over the years, this is becquerels, gross activity. It's not all strontium-90, there's other isotopes in there too, but it's a good indication of the patterns of strontium-90 decay. And because it's a longer lived isotope than a lot of the others that were in the fallout, the proportion of strontium-90 has been increasing. And so dry precipitation has more than dry deposition. They both follow the same pattern. This was the period of above ground testing. Remember that is 1954. You can see where 1950, we started testing just a couple years after that. And so in the end, I'm going to show you some evidence that we have levels as high as 1956 levels around some nuclear power plants in the US today. That wasn't at the peak, but that was coming up on the peak. Very, very problematic, certainly a lot higher than we expect from the sort of background decay. These were measurements around the Great Lakes when we studied Great Lake radionuclide facilities' impact on the environment. But this isn't the only place that strontium gets in the environment. So we find strontium-90 also in waste material from nuclear power plants. It's a fission product. We see it in when rods are reprocessed. We see it as a secondary nuclide that can be found in water and steam from power plants that can be released to the environment. There are certain levels of release that are allowed at nuclear power plants. They're supposed to be not contaminated or very, very small amounts of radioactivity, but who knows? Apparently sometimes stuff gets out. Then we also have accidents. And there can be small accidents, there can be large accidents. There was obviously a very large amount of strontium-90 released during the Chernobyl accident, during the Fukushima Daiichi accident, but probably more problematic to more people on a broader scale are smaller accidents that don't get the sort of large scale notice like a Chernobyl would get. And these happen in nuclear power plants every year. So some other examples of spills. So there's a place called the Savannah River site in South Carolina. It's a Department of Energy facility that does energy research and production. And there's the Hanford site, which we've talked about in Washington State, which is so contaminated. It was a former production facility. It's now a place where we store radioactive waste. We talked about MIAC last time. That's this region, one of the two above ground testing sites in the former Soviet Union. There's this Lake Karachay, which the Russians were just dumping stuff into. And so one of the main isotopes in that lake is strontium-90. Now there's a particular event that was kind of notorious and infamous, and again, during the Cold War, so we didn't really learn about it until later. But in 1957, there was an explosion in a high-level waste tank in Maya, and something like 20 million curies of fission products went into the environment. It's a huge, huge activity, right? And so about 5% of this was strontium-90 yttrium. So very, very high amount. There were people living in that region. Russians did very little to protect the people. And so, about 10% of this fallout went to an area kind of right around, the lake and where the explosion happened. And, something like 15,000 to 23,000 square kilometers were contaminated. A lot of people were evacuated to small towns and villages, but not everyone in the periphery. And it turns out that a lot of people were exposed and they could be tracked. The Russians did track them. They just didn't necessarily release that information to the public until later, or outside of Russia anyway. So I'll show you some data from that study of especially women of gestational or whatever childbearing age really take a lot of calcium from the environment and therefore strontium. And this is of course a fallout map for strontium-90 contamination at Chernobyl. We looked at this before. It's color coded. It's like a heat map. And so all these areas around the plant, remember the wind was kind of blowing this way for a while, then later the wind started to blow the other way, and there's deposition farther afield, but these are really high concentrations seen in the soil. And again, with a 30-year half-life, this stuff is still there today, something like 25% of it. And so when the Russians attacked Ukraine last year, and this is very close to the Russian border in the northeast. This is one of the first places they station their troops. They're digging in the soil and they're building whatever military guys build and exposing all their troops. It was something that hasn't really been discussed as much as it should. And this is a little bit of data from Fukushima Daiichi, another accident that we talked about a couple times ago in Japan. And what we're looking at here these are different areas in the ocean adjacent to the explosion. And so there's a couple of things. One thing that's plotted on here is this curve that's meant to represent how much strontium is coming in with rivers because of the global fallout. So we got the global fallout, it's happening everywhere, and measurements have been made in the rivers. And you can see, yeah, it had that peak, around 1960. For whatever reason, it's higher a little bit before 64 than after 64. I'm not exactly sure why, but anyway, this is the stuff that's washing into the bay from the land, and it's got some strontium in it. These are log scales, and these boxes just represent 3 different areas. And then these are measurements that were made, in the water, sort of independent of the accident, and then measurements made after the accident as well over here. And so you can see that, yeah, periodically they would go make measurements, and it would kind of follow what you would predict from the global fallout until they had the accident where they started to see higher levels, being emitted. And so this is only on this plot. We have shallow water and we have deep water. So some of the strontium gets exported down into the deeper water. And, there's a lot of questions about how much strontium was getting into food fish and how much was being incorporated into sea kelp and other plankton living in the water, etc. And so from this particular study, the estimate was that there wasn't as much as maybe people thought there was going to be because of the direct fallout to the ocean. And if they thought that strontium 90 would return to background concentrations in just a couple of years, mostly due to mixing, not so much due to radioactive decay. But so in this case, even though we know a lot of strontium went into the ocean, it's debatable how much of an impact there was, or maybe they missed the spot where there's an impact. I don't know, but the people do look at this kind of stuff. So now let's talk a little bit about how strontium gets into food webs, some environmental factors. So obviously strontium is falling out of the atmosphere, whether it's from the global fallout or one of these more localized sources. We also have strontium leaching out of medical waste, for instance, it's improperly stored. But it gets into soils and it behaves just like strontium, just like any other cation, calcium, sodium, whatever, it's going to bind onto players. So we have absorption and uptake, and the amount of strontium 90 is competing with regular non-radioactive strontium. So if you have a source with very high amount of strontium in the soil, maybe you have carbonate rocks, for instance, which then have high strontium concentrations, they'll dilute the amount of atmospheric fallout. If you have rocks with very low amount of strontium, like we have here, non-radioactive strontium, then the radioactive proportion, a greater amount of it can stick on the soils. So, they can be brought up into food webs, they stick into organic matter, they stick onto clays, they can get into, plant matter. They, to some extent, strontium will precipitate out with calcium carbonate. Like if we have a caliche zone in soils, we can find relatively high strontium concentrations there. And obviously some amount of strontium gets into the through flowing water and groundwater, but a lot of it is captured by soils and gets into plants, grasses, and trees, which animals eat, which we'll talk about in a second. It can also have impacts in the water, obviously getting into the food web, whether it's plankton, and bioaccumulating up through the food chain into fish, or sticking onto sediment particles and being exported to the sediment water interface and affecting benthic organisms. So if we look at plants that are commonly used as foodstuffs, wheat, corn, alfalfa, hay, oats, those kinds of things, they're particularly good at accumulating strontium. And a lot of it comes out of the soil by root uptake. That's sort of a common mechanism that we've thought about. It gets returned to the soil through leaf litter in cases that are non-agricultural. We're not pulling this stuff off and removing it from the landscape, but it tends to build up in agricultural environments. And in addition to the amount of strontium that's coming out of the soil, we're also receiving fallout, and some of this can land on the plant and be absorbed. And so certain plants have to be really good at bringing strontium out of the environment, and grasses tend to be one of them. So this is the main way that humans and other mammals can be exposed to strontium. Gets into the grass, as we just looked at. In our case, cows eat that grass, they produce milk, that milk is distributed to people, people drink it, gets into the human food chain. And there are also marine pathways from zooplankton to larger food organisms, but especially in this country, fish at the time when this was happening as a really high flux out of the environment, the marine products were not a common part of our the typical diet of an American, whereas cow's milk was, especially for children, especially in the 60s. And so, there was a lot of internal exposure to radioactive strontium by ingesting human milk. Some extent of inhalation exposure as well, but not nearly as much. Then we also have this external exposure, dermal contact, touching contaminated soils, or what have you. So ingestion and inhalation are more common for the average person today. There are locations where you could be externally exposed to a relatively high concentration or limited to around nuclear power plants or waste storage sites, etc. Or if you're receiving some kind of cancer treatment or something like that. But really, this ingestion is the main way. And it really was a main way. So there was monitoring of radioactivity levels in humans starting in like the very early 50s when the above ground testing happened. And people were finding really high concentrations of strontium-90 in people, especially concentrated in the bones. And so we started to see lots of leukemia and other bone cancers. And really it was the prevalence of strontium-90 contamination in the environment that led to the nuclear test ban treaty in the first place, especially the fact that many children were being exposed. So childhood cancer rates skyrocketed. And one of the interesting things about strontium, as I mentioned, is that it accumulates in the bones and then it decays to yttrium-90. It's got a relatively long half-life, but the yttrium-90 doesn't last that long. And so over time, it gets incorporated into the human body, and then it starts to produce some yttrium. And yttrium has a different chemistry. Yttrium is a +3 ion. It sits right next to strontium. And in some ways, it's similar to the element lanthanum that sits below it. And this accumulates in glandular tissues, pituitary gland, which obviously controls hormonal functions. And so it's sort of a double whammy when you get this material into the human body. It can really have long-lasting and pervasive impacts. So very early on, people had the idea that, it's getting into milk, milk's being fed to children, children lose baby teeth anyway. Why don't we start looking at strontium-90 in baby teeth? And so, people were already monitoring. They could see it in the bones of cows. They could see it in the milk. And there was this kind of alarming rise in childhood cancers in the 1950s. And so people started, like I say, studying baby teeth. There was one famous study published in '61, 60,000 baby teeth collected in the San Luis area. And, most people felt like it was their patriotic duty to give over their child's baby teeth to these kind of studies. And they showed the concentrations of strontium-90 increasing steadily throughout this period because of the above ground nuclear testing rate. This is, but before the test ban treaty, which went into effect in 1964. So we had each year higher and higher and higher concentrations. And then in '64, when they signed the treaty, that stopped. So that's why that treaty was signed in the first place in 1963, I would say, or one of the reasons. So what we find is that there was this peak in strontium-90 levels that we see in the milk, we see it in the baby teeth, and we start to see a decline as soon as the above ground testing ceases from the United States and a former Soviet Union. But unfortunately, there was the sort of damage was already done. There was a whole generation of kids that had very high increased disease risk because of this injection of strontium and the fact that they were drinking so much child's milk. And so cancer incidence in children under the age of 5 in various places, for instance, there was a study in Connecticut, can increase 40% between 1948 and 1950. So like in a 2-year period, it almost doubled between that and, excuse me, that 2-year period to this 2-year period. So think about a decade and a half, which is really a really incredible increase. But then after atmospheric testing, just in like another 5 years or so, it fell again by 30%. So we have a pretty good sense that there was a direct correlation there between the above ground testing. I mean, if you didn't have a reason to sort of not want to have nuclear weapons, in addition to all the destruction they caused, just the testing of them was causing really dramatic effects. This wasn't just restricted to places in the United States. This was a truly global fallout problem. So, you know, I'm going to show you a couple slides that show you correlations of cancer rates with injection rates. But, you know, this monitoring of the environment started to happen and continued pretty strong into the 1970s. So it wasn't just the US, Western Europe, even former Soviet Union. They were monitoring and seeing what the concentrations were like. And by the 70s, the levels were dropping a lot, you know, factors of 10 to 50. And so a lot of countries are like, maybe we don't have to do this quite so much anymore. And so, like, for instance, in the US, we sort of stopped incrementally, you know, in the 70s and into the early 80s. And so they sort of, you know, stopped monitoring, stopped having as much information. And it was interesting because we had declines in strontium 90 activities. And in a few places where we're still being monitored, these declines kind of bottomed out around 1975 and kept staying at sort of 1957 levels. People don't really think about it too much. We now know that there are other sources of strontium 90 to the environment, at least on a localized level. And I'll show you an example of that coming up at a nuclear power plant in Long Island, New York, where on a case-by-case basis, and this is also true in the region around the Great Lakes, there's enough strontium 90 that's put out by the nuclear fuel cycle and nuclear power plants that we're not getting back to above ground testing levels, but it's keeping levels higher than we would have expected from a single input to the atmosphere, then decayed away, as would have been the case if it was just fallout from above ground testing. So over here's a couple of plots. The red line is the same on both of these plots. It's cancer rates per 10,000 people in children in the United States. And this is picocurries per gram of radioactive strontium in children's teeth, and this is in adult teeth. And the patterns are pretty similar. I mean, they're basically, it's not a one-to-one correlation, but we can definitely see that during the peak of the nuclear testing in sort of 1962, 63, 64, and then the fallout, that the cancer rates drop pretty quickly. It's interesting that the cancer rates drop a little bit more quickly a couple of years earlier than the concentration in the teeth of and bones of the children and the adults, but nevertheless, that's a pretty reasonable correlation. Now, this is another plot showing you concentrations in New York. This is now moving much forward. This is 1945, so 60 to 65, that sort of peak, and coming into 1995. And during that period of time, it wasn't just childhood cancers. There were other things too. So this is birth weight, excuse me. So the percentage of children in New York State born with a low birth weight, I don't know what is defined as low, but before above ground testing, the typical value was somewhere between 6.5% and 7%, got up to about 9%. So obviously, you know, there are some people who are physiologically more susceptible to the contamination and would end up with cancer, but a much larger amount of the population was experiencing stunted growth during the gestational period. And that those low birth weights dropped again as the concentration in the atmosphere dropped from fallout. Interestingly enough, there was this later subsequent peak in the 80s that has been related to fallout from Chernobyl, half a world away. So, you know, and there are other, you know, things that can happen as well, but the cancer is obviously one of them. Now this, and the low birth weight is another. This is an example from Tetra River in former Soviet Union. This is not right near the Mayak plant or that Mayak site, I should say, but not that far away, several hundred kilometers. And this is looking at people, they weren't evacuated. This was farther than needed to be evacuated during that explosion in 1957. And this, excuse me, is looking at the amount of strontium-90 in the body of women of different ages, right? So 0, 5, 10, 15, 20 years. And what you see is that during this period of time where there's sort of post-puberty maturation of the sort of differentiated sexual organs, they're pulling in, and growth spurt, bones, etc., pulling in a lot of strontium from the environment, a lot more than older women or younger girls. And so just kind of illustrating the fact that as we've talked about before with toxicity, there are many biological factors which control how much a person takes up from the environment and how toxic they are or they aren't. But this was all data that wasn't released until much, much later. And many of these women were tracked. There's some data that was published in the in the late 2000s, which is referenced here, which kind of explains sort of the concentration and what the impacts were on those people. And they're very similar to what you find in the US. So, in the US, there's, we did that monitoring, as I said, which kind of petered out with the national monitoring by the 1970s to 1980s. There was the teeth studies, and those were really common in the 50s and 60s, and then they stopped in the 70s for the most part. There are some places that continue to do them, but it was a lot spottier, not as well, much geographic coverage of the United States. And it's also, important to note that there are other sources of strontium-90 to the environment, as I mentioned, mostly nuclear power, but also medical waste and medical procedures. And you think about it, every procedure that a doctor does, there's some factory somewhere that makes that stuff, right? They're making the strontium devices that are used to either generate external radioactivity or to use in medical imaging or whatever the purposes were. And so there could be waste at those plants, for instance. And interestingly enough, radioactive emissions from reactors have been linked to increased rates of leukemia in certain parts of the United States and in other countries. And although we don't know for certain that the culprit is strontium-90, is a very likely probability that it is a strontium-90. So this is just an example of a recent occurrence. So this is Long Island. That's where New York City is. That's Connecticut up there, and pretty far out Long Island, it's a place called Brookhaven National Lab. It's another one of these radioisotope research facilities. They don't do very much production, but around it there are a couple of nuclear power plants that have been in operation for a very long time. They kind of have older technology, and they've been operating research reactors since the 50s, power generating since the 60s, and there's these other two commercial power plants that are within about 70 miles of them, and they send particulate plumes. And so, people had the idea in the 80s, and they started to look in concentrations in child's teeth. They're like, no, we're starting to see some kind of high concentration. Maybe we should look at this. And so 1,700 teeth were received in 2000, of which they analyzed, not all of them, something like a third of them, for strontium-90 content, and they found lots of elevated content. In fact, what they found was that concentration in the teeth were as high as they had been in that original St. Louis study in children born in the sort of 1956 period, which was 5 years after above ground testing happened. It wasn't at the peak, but it was already well up the peak. It was a pretty high concentration. And we expected the global fallout concentration to have dropped and been very low by this point in time. To see those concentrations in these teeth, and again, it's not everywhere, it's just localized near a nuclear power plant. It's pretty hard to not implicate leakage from the power plant, even either not monitored or not reported leakage, and having an effect on children in the region. And there's a correlation between the strontium concentration or activity, measured here as a ratio to the grams of calcium. So amount of picocurie strontium 90 to the grams of calcium, and the cancer incidence rates. And you can see that the incidence rates, you would expect if it was, based just on the global fallout, that the incidence rates would have been dropping all through the 70s and 80s. But we can see here, we've got these very high incidence rates in the late 80s and early 90s, as if the fallout isn't falling out, which therefore implies that there's a local source. And I mean, if it isn't these either government facility or commercial nuclear power plants, then it has to be something else. And no one really knows what the something else could be. But it just goes to show you that I'm not trying to say that, the nuclear industry is always dangerous and always bad. And I mean, these may be incidental releases. The problem is that the way strontium behaves in the environment is it gets into the soil, it gets into the plants, it bioaccumulates, and it stays around, it persists. It's a major cation. It acts very much like calcium. And so it's not really washing through, and you can have slow, steady inputs into the environment and see relatively high concentrations in food. What's interesting though is that when we start to see concentrations going up and the incidence rates going up, it's not probably just bioaccumulation over time, because we've also got radioactive decay from fallout. Is probably an additional other source. And so this is why I say that, I probably wouldn't want to live near a nuclear power plant. It's just, I like nuclear power as much as anyone else, but given my choice, I also wouldn't live anywhere near an oil refinery because they are really bad. But people don't have that choice. They have to live where they have to live. And especially, based on economic factors. Anyway, I think this is the last slide. I thought I would spend all the time talking about strontium 90. And yeah, so as promised, it's kind of a short topic today. Are there any questions about this?
I don't have a question about this, but I have a question about the paper.
Okay, yeah, sure, shoot.
So for the article, how new does the newspaper article need to be, or does it matter?
Yeah, it doesn't have to be new. I don't care. I mean, if it's a couple of years old, 5 years old, it doesn't really matter. Unless someone has subsequently proven that that was wrong, that's okay with me.
Okay, thank you.
Yeah, did everyone hear that? Yeah, okay. And are there any other questions about the paper? Anyone has any? I want to emphasize, you have to make it really long, right? I don't want to read really, really long things, but I do want you to kind of give enough demonstration using whatever topic you've chosen in your example that you learn some stuff in the class, right? And so that's really the key thing. Show some insight, talk about the various things that we've talked about. I'm not going to refresh your memories because you've all lived through this, but we've covered a lot of different things in the class and about how contaminants behave in environments and how they get into environments, how they interact with organisms, et cetera, et cetera. So to the extent that not every topic has the same weighting factor of all these various things, some things will be more important for one or another topic, but just try and think big picture a little bit so that you can kind of demonstrate that you are now fully able to read any news account or listen to something on YouTube or wherever you get your news and interpret, or at least be prepared to ask questions about, do I believe this story, or what more do I want to know, or is this a problem? Where would I go for more information? What are the kinds of things I think should be playing into the story, et cetera? Because my impression of the coverage of environmental issues in the news is that they're oftentimes extremely superficial and overly dramatized, sort of oh no, this is the next thing that's going to get you. And what it does is it tends to make the general population sort of ignore it all, right? That's part of what happened with global warming. I think now, not so much anymore, but there were many years where everything seems sort of doomsday. And I think if you're informed enough to be able to think through what's really happening here, what do I think of the cause and effect and the issues, et cetera, and what more information do I want to know, then you'll be more prepared to be an informed citizen. So if there's no more questions, I will end it there.